So let me share my screen. So last week, we started with the introductory portion of Laplace transformation. And it was shared to you that this particular method was actually developed by a French mathematician. So it's another tool in determining solution of higher order differential equations as long as they are linear with constant coefficients. So it's easily handling the solution or determining the solution of higher order DE primarily because we need not worry about integration and differentiation because the differential equation is converted into an algebraic equation, as you can see in this flow chart. So it's being converted into an algebraic equation reliant on the formula that was shared to you as well. So last week we have started with Laplace transforms of basic functions. So there were 10, which also included the shifting of this basic function. So it was included in the 10 formulas. Then we also had the I think first 4 examples or 3 examples on the inversion of Laplace transformation, where in this time you're given a function of S and it is to be converted into a function of T. So once our DE, I will share to you the formula later in the Laplace transform of differential of derivatives, where you can apply to differential equations. You will process the said equation using algebra. And after that, once you already simplify the expression into a particular function of S, which has a numerator and a denominator, the last part is finished using inverse Laplace transformation. Okay, so the solution of higher order differential equations with constant coefficients is completed using both Laplace transformation and inverse Laplace transformation. Now, the primary definition of Laplace transformation was shared to you, and it's the integral of the product of that given function with the exponential function e raised to minus st integrated from 0 to infinity. It was also shared that if you're going to refer to textbooks on this and reference material, the representation of Laplace is the idealized letter L and the brace. Then inside the brace, you have the function of t. It converts it to a function of s. I'm referring to the function of t. For the inverse Laplace, it's also the italized capital letter L with the superscript -1. And instead of the brace, we use the bracket. So this time, you're given the function of s, and you are to determine the function of t. So these two, Laplace transformation and inverse Laplace transformation, are checks of each other. So Laplace transformation's answer can be checked using inverse Laplace transformation. The same way, inverse Laplace transformation's answer can be checked using Laplace transformation. So just like integral and differential calculus, which are inverses of each other, so each one can be a check for another. Yes. Okay, so wala gid siya ga transition. Thank you. So I'll go back to the main slide. So this is the one that I was sharing a while ago. Okay. And then you also discussed the linearity of Laplace transformation, and that is if your function of t has several terms, processing it requires that you apply the appropriate formula for each of your terms piece by piece. So transform the first term, then transform the second term. If you still have several terms after it, you can still perform Laplace transformation separately to those terms, and later on add the corresponding function of s. And since Laplace transformation is linear, we are not allowed to multiply transforms. So the example I gave this last meeting is regarding the sine and cosine function. So let's say if your f1 of t is a sine function, and if your f2 of t is a cosine function, you cannot determine the Laplace transform of the product of the two by simply multiplying their individual transforms. It's not allowed. So what you're going to do, you are rather to convert your sine t, cosine t expression using identities. That way it can be written in just one function. And then, of course, apply the appropriate formula to that particular single function only. So we don't have multiplication of Laplace transform. So if there are functions that are not among the 10 functions that were provided to you in the formula, then don't really, let's say, expect that all conceivable functions that you have in mind can have a Laplace transformation. Because e raised to the tangent of t or the ln of cosine t does not have a function of s, meaning they are not transformable. So Laplace transform cannot be performed on them. So only for those complicated expression that can be converted or translated to any of the 10 basic functions, then we'll have a function of s. I also shared to you last meeting regarding the concept of the unit step function represented as the u of t. So this is a function which has a value of 1 when t is equal or greater than 0. So you can see the value of the function here is constant at 1 when t is greater or equal to 0. Now this unit step function is the basis in determining Laplace transforms of constants. So the unit step function u of t, in here, if I will take out the 1, I'll place here the u of t, e raised to minus st, will have a Laplace transform of 1 over s based on the process of integration that you will do here. So your u of t is equivalent to 1 as long as t is equal or greater than 0. And since your limit here starts with 0, starting with 0 to infinity, then that applies to your given function as well. So you will have here to perform the integral of e raised to minus st. And since you know how to integrate, and I'm sure you do, then when you perform integration and substitute the limits, this is the answer. So this applies now not only to u of t, which has a value of 1, but to all constants that you wish to convert to the function of s. So if you're after the Laplace transform of 25, for example, then your function of s for that would be 25 over s. Okay? Now, another formula that was shared to you using showing the derivation rather of its Laplace transformation is the e raised to negative alpha t. So this is the exponential function, and this is its corresponding Laplace transformation. Again, you perform here product. When you have the product of two, the same exponential expression, the same in the sense that they have the same base, you add the exponents and then apply the corresponding rule of integration. And in this case, the Laplace transform of e raised to minus alpha t is just 1 over s plus alpha. If this is negative alpha, this becomes plus alpha. If this is positive alpha, this becomes negative alpha. Actually, in common references, it's actually e raised to at, where the formula is 1 over s minus a. And since it's negative, so that now becomes positive. The s minus a negative number becomes s plus that particular number. So this will be your formula for the Laplace transform of an exponential function. All you have to do is take note of the constant of the real quantity that appears in the argument of the exponential function, and then place it here in the formula. Now, the rest of the functions are written here in the table. Now, 3 of which are already the shifting of the standard 3 functions. So your standard sine and cosine function have these formulas, but once shifted, all the s that appears in the formula will be changed to s plus alpha. It's because your alpha here is negative in the two exponential function. The same principle applies when you have your t raised to n and it's being multiplied to e raised to minus alpha t. You're going to shift the s by subtracting from it the value of the alpha. So it becomes now in here positive because your alpha is negative. So these are our 10 basic formula for Laplace transformation. In your advanced engineering mathematics later on, there might be added formulas to this. So I did not include here the hyperbolic sine and the hyperbolic cosine, but we do have those two. Okay, this one is the Dirac delta function. It is the only function of t here in the 10 functions which does not have an s in its Laplace transformation. So your Dirac delta function has a Laplace of 1. If this Dirac delta function has a magnitude here, let's say for example 10 Dirac delta of t, then this will also be 10. We apply the same principle we do with integral, that whenever your function has a constant multiplied to it, you set aside the constant and just apply the corresponding formula to the function itself. And then whatever is your answer to that, you just multiply the constant which you have set aside. So it's the same thing in here. So this is understood to be 1, so that is why you have 1 here. If this is a 12, this should be a 12. So no s will appear in the function of s for this particular function. Now we have this example for the Laplace transform of 50 u of t, or simply a 50 because your u of t is 1. So its Laplace transformation is 50 over s using this formula 1 over s. Okay. Another one is for the sine function, this time which has an exponential function multiplied to it. So what you do, you set aside the constant 5 and then substitute the formula for e raised to minus 2t sine of 4t. So for the sine, the numerator is omega, the constant that is appearing in the argument of your sine, s plus, since it's negative, alpha squared plus omega squared. So this is our denominator now. The rest is your algebra after you have simplified your denominator. So don't forget to multiply your answer here in your Laplace transformation by this constant 5. Okay, now we also have this one for the cosine and the exponential function. The difference between the cosine and the sine function is what appears in the numerator of the function of s. So for both, the denominator is s squared plus omega squared, or the w squared. But in the case of the cosine, it's not the omega, it's the s that appears in the numerator. So you have this one here. In the case of the exponential function, it has a Laplace transform similar to the unit step function in which the numerator is 1. The denominator is s plus alpha because you have here negative alpha. And this is your simplified answer for the p of s of this p of t. Okay, the function of s for this p of t expression. Now, we do have Laplace transforms and we do have inverse Laplace transformation. Inverse Laplace transformation, however, requires something extra because you need to render the given function of s standard. It has to look standard or fundamental based on the one that you have that is written in the table of formulas. So if your function of s does not look standard based on a particular function of t, you have to make it look standard. Normally, it will only require multiplication and division by a constant, or it may require you to complete the square in the case of a quadratic denominator in which the roots are, shall we say, complex and conjugate in nature. Okay, so to review, this is what is presented to you last meeting. So the inverse Laplace of 5 over s, you take out the 5 and you just process the inverse Laplace of 1 over s. So the inverse Laplace of 1 over s is 1. So then that 1 is multiplied to 5, giving you 5. Now for a denominator, which is an s raised to a particular exponent, it was also pointed out that it must have been coming from a function of t raised to n. Because if it's a function of t raised to n, your s and the denominator is raised to a particular exponent. And the numerator is just the n factorial taken from your denominator exponent minus 1. So in this case, class, this is 2 minus 1, it's 1. So meaning the numerator here is just 1 factorial. So if you set aside the 12, what remains here is 1 over s squared, which is actually the Laplace transform of t. Now, this one is easy because if we set aside the 8, what remains is 1 over s plus 3. Whenever your function of s in the denominator has an s minus a constant or s plus a constant, that tells you that it came from an exponential function. Because the numerator for the Laplace of an exponential function is always 1. If you invert the 1 over s plus 3 here, that would be e raised to minus 3t. So you just multiplied it again to 8, which you set aside. How do you check whether your f of t here is correct? Take the Laplace transform of this. It should give you the given function of s. Okay, so that's what you do. Now, in the case of the sine function, in the here, you look at the form of the denominator. So it's s squared plus a constant. So this could be s squared plus omega squared. So from in here, you could see that your omega is 10 here in the 100. So if your omega is 10 and the numerator should be a constant, the numerator should be that omega. It should be that 10. So since you have 200 here, you take out the 10 from the 200 by division. So 200 divided by 10, that would leave you 20. You need to have the standard function of s for the sine function here. That is why you manipulated your original function of s to look like it's the standard function of s of a previously thought sine function. Since we know already that omega is 10, so we made sure that this is 10 here. So the answer for this when inverted is sine 10t, and you just multiply it by 20. Now again, if you wish to check, get the Laplace transform of this and you will go back to the original function of s or the given function of s. Now we've covered that last meeting. I think this is where we ended. Your function of s as a denominator, which is expanded in expanded quadratic form, but once factored will yield complex conjugate roots. Like this one, this is the complex conjugate roots of this. Whenever you have such a particular function of s, you use completing the square in your denominator. You complete the square of the denominator. So if you notice, class, since we have done inversion, we always start looking at the denominator. The denominator points out to us, or let us think ahead of the probable function of t where that given function of s came from. So it's always the denominator where we start off. Okay, in here we also started with the denominator. So going back to this, the same way we're going to start with the denominator. And I mentioned that you are to do completing the square. It was shown to you in the Jamboard last meeting. So if you're going to complete the square of s squared plus 6s, the constant that will complete it is 3 squared. You take the 3 from 6 divided by 2. Okay, it's always like that. The middle term in your quadratic polynomial is divided by 2 and being squared to give you the constant to be added to it to make it a perfect square. Now, if you have this would simply be s squared 6s plus 9, and you have the original 13. So what would make it 13? You add 4. So in this process, you have the perfect square equivalent of s squared plus 6s plus 9, which is s plus 3 quantity squared, and the perfect square equivalent of 4, which is 2 squared. So now you have written this one to this, which is now consisting of a sum of two perfect squares. Okay, now after that, since you already completed the square of the denominator, make sure that the shifting that appears in the denominator, let's say this is your denominator, never mind the second fraction for now, is s plus 3. You have no choice but to reflect the same shifting in the numerator. It's on the primary premise class that whenever there is already shifting in your standard function, all the s in the function of s of that particular function will be shifted. And since your numerator in the original function here has an s, you have to reflect that same shifting. So we did just that. It's just like you copied this one in here. So it's now s plus 3. However, you could see that this is now 8s plus 24. The original numerator is just 8s plus 4. So what you do, you have this original number, 4, the constant, and you have here 24. So you subtract 24. If you do that, you have here 24 minus 20. That would give you the 4. The original 4, which is to be added to 8s. Now, in here, they were already separated. Now, you may wonder why it's already separated, because when you do inversion class, you don't invert like you have a shifting in the s, and in that same numerator, you also have a constant. So view this as one function that was shifted, and this is another function that was shifted. If you're going to add these two, you're still going to come back to the original function that was given. Okay, so all you just did is manipulate that way. The function of s that you will invert is already standard based on what you could see in the table if you're going to apply the formulas. So in this case, you could see here that you have an 8. So you just easily place the 8 before the inverse Laplace of this expression. You have an s in the numerator and you have an s squared and a, shall I say, a constant squared in the denominator. That's a cosine. If you don't have the shifting, it's a cosine of 2t taken from the 2 here. But since you have here a plus 3, you have to account for it. Meaning you have to account for the shifting by multiplying the cosine 2t by e raised to minus 3t. The alpha that appears in here. And then multiply it by 8. In this part here, what you have originally is negative 20. If you should have a constant in the numerator, just like our example here, this is a constant, you make sure that this constant should be the omega in the denominator. So we apply that same principle here. Your omega here in the denominator is 2, so your constant here should be a 2. So then you have a remaining 10 that will not be a part of your function of s that should be inverted. So what should be only inverted here is 2 over the quantity s plus 3 squared plus 2 squared. This 2 over s plus 3 squared plus 2 squared is this one. And you just multiply it by 10. How would you know that what you have here is correct? Perform Laplace transformation here, simplify, you will go back to your given function of s. Okay, so this we covered last week in our intro to Laplace transformation. So for this afternoon, we will now think of inverting function of s expression in which both the numerator, you can see here an n, and the denominator are, shall I say, polynomials in form. Okay, now you may wonder, where will we get this particular expression, Miss Ali? We are going to study the solution of higher order linear differential equations with constant coefficient. And where will we get this particular expression? This particular expression actually, class, will come from the DE after you already perform Laplace transformation on all the derivatives present in your DE and all the function of t's that will be present together with those derivatives. So this will be the simplified expression of that particular algebraic expression that was mentioned in the first step of finding solutions of higher order DE. So you have a numerator and you have a denominator because your function of S, your final function of S will always be at all times rational in form. Rational fraction siya. May numerator siya kag may denominator. So just like what we did in the previous function of S, which we have inverted, we always focus on what is written in the denominator. Notice that the numerator is still written as n of S, but the denominator now is factored. Why factor the denominator? You're going to use the principle that you have applied in method of partial fractions in integral calculus, and the same principle that you have applied in method of undetermined coefficients. You use partial fractions there in here. So the next step that you will do is factor the denominator of the final function of S that you have to invert. Since inversion is the last step in finding the solution of your DE, you have to make sure before you do inversion that the denominator of your function of S is factored. So in this case, it's now factored. And then you have to go back to the previously learned principles regarding the factors of your polynomial denominator when you use the method of partial fractions. So the factors can be either linear, repeated linear, or they can be quadratic, expanded quadratic, or repeated expanded quadratic. These are the scenarios that you have. Now, when we speak of the actual application of Laplace transformation later on in controls, we refer to these roots of the D of S as the poles. So it's named differently, but it's the same thing. You're going to find the roots or the poles of your function. So your poles can either be real, they can be complex, just like the ones I've shown to you a while ago. Complex siya. It has a real and an imaginary part. They can be real poles of multiple order. This is just the term that is used in controls, but these real poles of multiple order simply refers to class to real repeated roots. Ang tawag lang na diya sa iya is multiple order, meaning, for example, you have an S, and then for example, you have an S cube that is to be viewed as S squared, and S cubed. So when you write the three partial fractions equivalent to the sum of three partial fractions equivalent to just 1 over S cubed, amo na siya ang pagkasulat. A over S, B over S squared, plus C over S cubed. I hope you can still remember because we just finished it a few weeks ago. So that's it when you have repeated. So if your linear root is not as simple as S cubed, for example, it's S minus 1 quantity squared, when you write its equivalent partial fractions, you write 1 over S, A over S minus 1, and then you have plus B over S minus 1 squared. If it's cubed, then you have another partial fraction, C over S minus 1 quantity raised to 3. I hope I make sense because that's what you did in your calculus and your topic in undetermined coefficients. So if you have repeated roots, linear, they are referred to in here as real poles of multiple order. It could even be complex poles of multiple order. So meaning, you have, let's say, S squared plus 3S plus 9 quantity squared. So that's an expanded quadratic factor, but it's repeated, kaya naka-ratio sa 2. So if you have that, then you have to properly represent it also when you write your method of partial fractions. As for pure imaginary poles class, these imaginary poles we will not include here for now because I did not include the hyperbolic function. So we will just have real repeated roots or real complex roots, but no pure imaginary roots because that would be yielding the hyperbolic sine and hyperbolic cosine function. Recall that when you reach your advanced engineering mathematics next semester, okay? Or not recall, but rather it would be discussed by your teacher there, okay? Now, in the next successive slides, I will show to you, actually, it's a review of what you've been doing in the past regarding how you find the, we call it in DE, the values of the undetermined coefficients. In your integral calculus, you find the value of the coefficients prior to you integrating the partial fractions. What are these partial fractions? The partial fraction equivalent of your original fraction. Now, to me, for it to be better discussed and for me to make sense, I'll have this specific example. Let's say this is your function of S, and you are required to invert this. Of course, when you'll have this inverted, you cannot use any more completing the square for this one because we only use, remember this, we only use completing the square when our denominator is not factorable. In this case, our quadratic denominator is factorable. So what are its factors? So it's S plus 1 and S plus 2. We don't do anything on what's written in our numerator. Now, in your method of undetermined coefficients or in your integral calculus, when you find these coefficients, we used to write this as A and you used to write this as B. You do the same thing in here. You can label it as A sub 1, A sub 2, or A, B, C, or X, Y, Z. It depends on you as long as you find these coefficients. The same procedure you will apply when you did find the coefficients in your method of undetermined coefficients prior to you, in this case, prior to you applying the inverse Laplace transform to your given function of S. Now, how do you find the value of A and B? Very simple, right? In our case, I used equating coefficients, if you can recall. But you can also set a value for one of the S here. If you set its value to -1, one of the two partial fractions that you will have here will be 0 because your S is now -1, so this one becomes 0. So you will be left with the second partial fraction. That's how you do. I think you do that in your integral calculus 10. I'm not sure how was it explained to you by your teacher, but nonetheless, you can do that or you can equate coefficients. To cut the explanation, since you know how to do this, you already learned this twice. You find the values of A and A1 and A2. In this case, that's 5. For A2, that's -4. You just substitute it here in the original, in the original representation of the partial fractions. We call this class the partial fractions. The sum of these partial fractions is actually equivalent to this. You see this equal sign? So the reason why we have to write it in this form, that way we can find the Laplace transform of this original function of S, which is also like this. So when you substitute the 5 here and the -4 in here, as presented in here, you could see that you can now have this readily inverted. If you will invert this one, since your denominator contains an S plus 1 and an S plus 2, that tells you that you must be having an exponential function for your function of t. Because we know that if you're going to get the Laplace transform of this, we will go back to this function of S where we started. I hope you get me. If you're going to have this expanded using algebra and combine using tools in algebra, you will go back to this. This will be the resulting expression that you have. So the reason why we convert it into the sum of its partial fraction, as such the term method of partial fractions, is for us to be able to have it inverted like this one. Okay? Now this is a case when your function of s has a d of s or a denominator which is factorable, and the roots or the poles are real. And if we will compare it to the method of undetermined coefficients, they are real and unique. So wala kita sang may repeat because they are unique from each other. Okay? Now, another consequence probably, or rather example that we can have for this is this one. You have a combination, so good for this because it's already in factored form. But when you're going to process this using the method of partial fractions, since your denominator when expanded is 4th degree, 2nd degree, 3rd degree, 4th degree, expect that you should have 4 partial fractions. 4 partial fractions. 1 each for these linear factors and 2 for this expanded quadratic factor. If you recall, this quadratic factor has a numerator which is as plus b. Or if you'll have this one as a1 and we'll have this one as a2, then you can have here as plus b for the numerator of this factor alone. So the numerator is 2. So if you're going to split it, then that would be still equivalent to 2 fractions already. So all in all, you will have 4 fractions. In the solution that is illustrated here, what was determined first is the coefficient, or are the coefficients of the first 2 linear factors. So finding that, you use equating coefficients or substituting a value for s gives you a to be 25, a sub 1 that is, and a sub 2 to be negative 10. If you substitute these two in these 2 partial fractions, it's so easy to invert because again, these 2 are just exponential. So you could see you have this one now. The last one, wherein you have this, s squared plus bs plus c form, an expanded quadratic denominator, your numerator class has to be an as plus b. And by the way, just like when I emphasize it in the method of undetermined coefficients, and I think in your calculus then, it need not be that this is processed last. It could be even processed first and these two last, as long as we find the coefficients, the correct coefficients in the numerator of these factors here. Okay, so in this case, if we do that for our quadratic factor, for one of our factors in the denominator, which is quadratic, the value of the a and the b are negative 25 and negative 15. Since we know already the first two, we just copy them and affix this negative 25 and negative 15 here in the numerator. What do you think will be the last step? The last step is for you to apply the same procedure we did a while ago, completing the square of this denominator. That way we can get the corresponding functions of t's for this particular function of s. How do we do that? So you complete the square of your denominator. So s squared plus 2s plus 1. 2 divided by 2 is 1 squared, that's 1. So you have originally 5, so you have to add 4 to it. So 4 in the perfect square form is 2 squared. So now your denominator is written as s plus 1 quantity squared plus 2 squared. Now, what we did, we make sure that, a while ago, we made sure that the shifting in the denominator is the same in the numerator. Copy the constant. You have no choice because it's originally 15, negative 15s. So you have to affix that one here and copy the shifting in the denominator. If you have this, you have negative 15s minus 15. The original is minus 25. What do you lack? Minus 10. If you add these two fractions, it's still equivalent to this one, the original. So now your minus 10 was just written in a manner that way. If we have a constant in our numerator and our denominator is an s squared plus a constant, or a shifted s squared plus a constant, the numerator should be the constant that appears in the denominator. I'm referring to the omega. So kung omega mo didiri 2, so your numerator should also have a 2. So this is supposed to be negative 10, so it's now negative 5 times 2. And then invert. Now this now is your function of t for what? For the original function of s. Now, if you wish to check, you can. Where is it? You can check whether this is really correct. You get the Laplace transform of all of this, simplify, and you should be getting the original or the given function of s. Now, this particular process of finding the function of t is really, really very useful when you finish the solution of your higher order linear differential equation with constant coefficient. Now, what you have here in the first two examples are linear roots and quadratic roots. I think I have here wherein it's being repeated. So you see this one here? Second order real poles, wherein the poles or the roots are being repeated. So when you write its equivalent partial fractions, it's like this. For example, this one, example 10. You have a 60 over s times s plus 2 squared. If you look at this, actually all of these are linear roots. Linear in the sense that this is linear. You don't view this as quadratic. This is repeated linear, or we call this multiple poles. Linear via multiple poles. Multiple in the sense na hindi lang isa, kundi kaduha siya natabo kay nag-squared siya. So sa method of partial fractions, how we do it? We repeat it. We repeat these roots depending on the power or the exponent to which this root is raised to. So if this is cube, you should have another one here. It should be a c sub 3 over s plus 2 quantity cube because you repeated it. The procedure would still be the same as the method of undetermined coefficients in finding a, c sub 1, and c sub 2. So in this case, you have these values here. And when you invert, the same thing. 15 over s is 15. This s plus 2 raised to 2 tells you that your standard t raised to n was already shifted. Because if it was not shifted, kung wala siya gin-shift, wala na di plus 2. Igaling kay gin-shift siya, so amo na siya nga ang t ninyo, may multiplier na nga e raised to minus 2t. This accounts for the shifting that happened in here, in the s plus 2. So it's accounted for by this exponential function. So since we have only one factorial in the numerator, since our n is 2, so 2 minus 1, that would be your n. So 1 factorial. So you have 30t e raised to minus 2t. For this one, it's easy because it was not raised to any particular exponent. So this is just but an exponential function. And you have this as the 15. The rest is just your algebra. So you have I think what was factored out in the second and in the third term is your 15 e raised to minus 2t because it was set aside in here. And you will have 1 for this and you will have plus 2t for this one because you have your negative already. Okay? Now, you know how to take Laplace transformation. You know how to take inverse Laplace transformation. So the remaining part is knowing the Laplace transforms of derivatives. How do we get the Laplace transforms of derivatives? Now you may wonder, why learn the Laplace transforms of derivatives? Your differential equation have the presence of the derivatives. So how will you be able to determine Laplace, the solution of your higher order DE if you do not know the Laplace transform of these derivatives. That's what you're going to learn, supposed to be on Wednesday. So I'm going to have it recorded, and then after that I will apply it to finding. I will apply this entire module now to finding the solution of linear higher order differential equations with constant coefficients. So the last part, I think probably another hour or 30 minutes will do, because anyway, the process of inversion is just a repetition of what you've learned in the past regarding method of partial fractions. And that's it. You now have another technique in finding solutions of higher order DE. And that's Laplace transformation. Okay, I will have that recorded. This one I will share to you right away once I've already shared the link. And that one I will record within the day, or the most is tomorrow. That way you can listen to it. And that one will be included in the exam. So this entire module will be included in the exam. And it will be given as your quiz number 4. Okay. Do you have any questions for now to what we have discussed?